Hello everybody, thank you for tuning in. I'm very happy to be here today talking to you a little bit about the results we've been obtaining on cataloging tremor signals at the Lightning Dock Geothermal field in New Mexico. Of course, I want to acknowledge my co-authors for this project, Alan Husker, who is my postdoc supervisor at Caltech, KJ Im, who's a postdoc here at Caltech working with Jean-Philippe, and Joel Edwards, who is the point of contact at Zanskar. The Lightning Dock geothermal field in New Mexico contains a high temperature resource of about 150 degrees Celsius at 0.7 kilometers depth. It was first developed by Circ Energy starting in 2013 and is currently producing over 10 megawatts of energy. And the data that we've been using is from a 1200 geophone seismic array that was deployed for 3 weeks with its original purpose to better image and assess the controlling fracture networks. So this here on the left shows the seismic array deployed for these 3 weeks. And in particular, sort of want to show these blue squares, which corresponds on the injection wells. So you can see they're on the west and the east of the array. And the producing wells are as red squares, and it's right in the center of the array. We've shown some of these results in the past, but they've always been on a limited subset of data. And now, sort of what we're going to be showing in this presentation is using the full 3 weeks of data. All right, so what are some of the interesting signals that we've been seeing? So this here shows a 1-hour record. The top part shows the seismic trace, and the bottom is a spectrogram. For those of you that may not be aware, a spectrogram is a way to represent time series data where the x-axis is time, in this case in seconds, so this is 1 hour of data. The y-axis is frequency in hertz, and the color represents the spectrogram power. And you can kind of see these sort of arcing traces that are essentially microtremors that are present through many parts of our data. And so what we were really interested in was the following research questions. How many types of signals are there? You know, this is one type. Are there other types? And when and where do these signals occur? And how do they relate to what's going on in the geothermal field? And lastly, what are the physical mechanisms driving these observations? So I will be talking a little bit about each point in some detail. Not everything is going to be covered here. For those things that I do not cover, please come to the group presentation on September 20th at 10:30 in the morning. And September 20th is day 1. What makes this project so challenging is sort of the data quality and particularly the noise that you can have at a geothermal field. So believe it or not, the trace that I showed before is one of the cleanest traces we have to work with. This here are from a different hour, and these are 2 different instruments. And you can see that this is very, very messy in the spectrogram. And if you kind of take a look at this one, there might be something here that might be interesting. There's definitely these little traces right here. On this particular trace, it's kind of hard to see much of anything. This sort of peculiar trace still pops out, but all in all, and these types of recordings are extremely saturated with noise. And we tried to kind of approach each instrument individually at first, but we weren't getting much success on something that was very robust, that could work for all the particular instruments and noise types, if you will. So what we ended up doing was assessing types of signals by stacking clipped spectrograms. So we take each of these spectrograms, we would clip them above a certain value that we deemed sort of the noise floor, if you will, and stacked all of them together. The result after stacking can be quite striking. So this here is the same trace that I showed before with the sort of the 2 stations, but now stacked using clipped spectrograms across all 1200 stations. And so you can see that you have these sort of very transient features right here that really pop out, as well as these sort of very emergent convex traces in the spectrogram. After we processed and looked at the entire record of those 3 weeks, we found that there were 2 different types of traces, what we called impulsive signals and emergent signals. So both of those were displayed on the previous slide for that same hour. And what you have is here, emergent is a very sort of tremor-like, and this is sort of the convex shape that in the spectrum they're seeing before. It's very sort of low amplitude. And then you have these sort of very thin impulsive signals in the spectrogram that are sort of very, very narrow band. And what we actually saw, and we sort of presented on this a little while ago back in April, was that unfortunately these impulsive signals, as cool as they are actually not given by real mechanisms. They are due to geothermal machinery. And this will sort of be shown again a little bit later on in the presentation. So moving on, if we want to try to understand when and how these signals are happening, we first have to catalog them. Before we could catalog the signals, we had to do a frequency average removal in the spectrogram. So what that means is that starting from this stacked and clipped spectrogram, we would find the average value at each frequency and remove it. The big advantage of this is that it would allow us to see for a lot of these emergent signals really when they were beginning and ending, which was more ambiguous in the original spectrogram. We played around with various ways to do automatic picking, but it ended up being a lot more trouble than it was worth. So we did this manually. There's usually a video that accompanies this, but it doesn't work in recording mode in PowerPoint. But the gist of it is essentially that you as the user will draw literal sort of boxes in the spectrograms for both impulsive and emergent signals that tell you what the frequency and time bounds are. From the manual picks, we were then able to obtain various parameters for each event, including signal duration, frequency span, min and max frequencies, mean energy, and max energy. Overall, we were able to catalog a total of 255 events, 110 of which were emergent and 145 impulsive events. And we assigned an event ID to each event and combined it all in a catalog and saved sort of images for each of the events we could go back to later. And so these little red lines represent the maximum energy for the trace that was used to obtain the mean energy and max energy calculations. I would be a bit remiss if I didn't show you some of the cool events that we found. So this is approximately about 15 minutes long. And sort of this is very close to what I was showing earlier. We have all these sort of beautiful harmonics that go all the way up to almost 130 hertz that really show very sort of tremor-like energy. Now, this other event is quite cool because it doesn't have a single sort of convex shape, but it actually goes down and goes back up and goes down again and back up again, and over the course of 30 minutes. And again, we're a little bit over 120 hertz right now. I also wanted to highlight this sort of very horizontal streak right here of energy, which is an artifact that was not able to be removed by our frequency average. And this is what makes a lot of the automatic detections so challenging to use, because traces like this would trigger the algorithm to imagine that this is an important segment of energy, when in reality it's just an artifact. And lastly, I kind of wanted to show this other event because it's quite long. I think this is the longest event that we have. It's over an hour, and you can see each sort of individual cycle. But what's really neat about this is sort of draw attention to sort of the first peak here and last peak here, is that the lengths of the peaks are actually changing in time, which I thought was quite unique and cool. Here is some information on both emergent and impulsive events labeled as histograms, with emergent events being blue and impulsive events being red. What we have here are the variables duration, frequency span, mean energy, and max energy. And what we can see by the distribution within the histograms is that emergent events are typically of longer duration, as much as an hour or more, typically have lower energy and have a smaller frequency span than impulsive events. Again, impulsive events, unfortunately, are caused by non-natural processes. So this is a plot showing the cumulative flow and the number of stations alongside duration. The x-axis is time, displayed by month and day. So what I want to call this is sort of each individual trace first. So in gray, we have the number of stations from 992 to over 1,000. And the cumulative flow is displayed in both injection and production, with injection being in blue and production being in red. You can see it sort of ramps up starting at August 5th. Now the duration here, the scatter plots are with blue being emergent events and red being impulsive events. If you look at when these impulsive events are occurring, you will notice they occur during the day. This is actually UTC time, but during the actual day within the geothermal field. So they're not occurring at night. They're only occurring when there's work happening at the geothermal field. What we can also see, though, is in the emergent events, which is what we're primarily interested in, there seems to be an increase in duration coinciding with increased injection at the field at a little bit before August 5th. What this plot shows are the emergence max energy and emergence mean energy with superposed injection and production flows that I showed before. And what we're particularly interested in was whether or not the energy increased during periods of increased activity. Unfortunately, what we ended up seeing was that, yes, there was an increase right after August 5th, but there didn't seem to be one after August 13th, after the injection increased a little bit more. So we would kind of need a little bit more data to convincingly say whether or not energy increased. We were also interested in finding out whether or not the minimum and maximum frequency bounds of the emergence events changed according to the production and injection schedule. So here again is the number of stations here at the top. And then we have minimum frequency in hertz on the y-axis and maximum frequency is hertz on the y-axis here in the third subplot through time. And we found that this was not the case. So it doesn't seem like the number of harmonics are changing depending on what's going on with injection and production. So we've now discussed when these signals occur and how they relate to production processes, but we still haven't addressed the where. And our collaborators at Zanskar have been able to use the catalog times that we provided to locate these tremor signals using back projection. And so I'll let them talk about it. Please tune in on September 20th at 10:30 in the morning for those results. We now have possibly the most important question to answer, which is, what do these signals represent of the systems? What are the mechanisms that are driving these observations? And for mechanisms, we are favoring one proposed by KJ and Jean-Philippe in their 2021 EPSL paper, which is friction-induced inertial vibrations. The mechanism is going to be described a little bit more in detail in our group presentation on day one of the conference. But we want to kind of leave you with an image that shows why we think that this mechanism might be at play here. And to do so, what we're going to do is going to downsample the data. So here is a 1 hour spectrogram trace that we've seen, and this is at the full 500 samples per second. Now this is the second trace, the same trace, but now taken down to 100 samples per second. Now you can already start to see that there's sort of these tremor-like signals that are a little bit more apparent here in the downsampled than they were in the fully sampled data. These are stacks of the clipped spectrograms as we've shown earlier in the presentation. And this is the top plot is for 500 samples per second, and the bottom is for 100 samples per second. Now you can see these sort of really striking features in the lower frequencies that were present here in the top plot, but nowhere near as clearly defined. It's actually quite interesting because it's a lot easier to see in this downsampled plots where these tremors begin and when they end. Now for friction-induced inertial vibrations, this mechanism is not very different than a creaking door hinge. And so what we're going to do now is we're going to take a look from a video provided by KJ, which kind of shows this mechanism at play. Let's now take a look at a spectrogram of the audio from that same clip. As you can see, there's a lot of interesting similarities between what we see in the lower frequencies of these tremor signals and what is seen in the door hinge mechanism. And so this friction-induced inertial vibrations is a mechanism we're currently exploring in depth for what could be going on at the geothermal field. Thank you so much for taking the time to listen to this presentation, and many thanks, of course, to Circ Energy for hosting the experiment and allowing this research to be published. Hope to see all of you at the group presentation on September 20th.